Right. So where are we? I think before we continue from what we have stopped, last Wednesday. Okay. So just a glance of a recap of what we have learned. So last Wednesday, we have learned how to interpret a phase diagram. Obviously, there's a few rules that you need to follow. Okay. Rule number one, the number and the types of phases can be identified if you know the number and the types of phases present. Okay. And then rule number two, the composition of phases. So if we know the temperature and the composition, then we can know the composition of each phase. And finally, the weight fractions of phases. It can be determined if we know the temperature and also the initial composition, right? So normally for the weight fractions, if let's say that it exists in one individual phase, then it shouldn't be a problem because it will be 100% of the respective phases. But if it is in a mixture, like for example, you have I think element or the phase is actually at liquid plus alpha, then you know that the weight fractions or the amount need to be reported for both phases. Then we also have looked into the phase rule. This is actually a guide for you guys to determine what would be the weight fractions of a liquid and also the weight fractions of a solid, right? And we also have looked into the some examples, I think using a phase diagram, the one that we have seen quite a lot using copper and nickel. And I think for this example, we are looking at magnesium silicate and also iron silicate. And we also have looked again into this example. So I really hope that you guys are able to understand how you can actually read and how you can determine the weight fractions. And I think most of this lecture were recorded. And if you still didn't understand, you can watch back the videos and try to to understand and to get the idea how you can determine all these things. And I think finally, last Wednesday, we stopped at the microstructure of an isomorphous system. The first one that we have is actually at equilibrium cooling. So the one that I told you before is that when we produce alloy, it is possible for that alloy to exist either in equilibrium, alloys or non-equilibrium alloys. This is basically with respect to the cooling process. As I said, for equilibrium cooling, it will be a very slow cooling. After you melt the elements and you mix it together, the element will be solidified naturally. There's no like other things or other tools being introduced to help to facilitate the cooling process. Then the phase will be maintained as in equilibrium, right? So for today, we are looking at non-equilibrium cooling. Okay, so what does it mean by non-equilibrium cooling? Non-equilibrium cooling is where the isomorphous alloy produced is basically being facilitated with something that can actually accelerate the cooling process. For example, okay, after you have mixed the molten liquid together, you can see that maybe there's a assistance of maybe using refrigeration system, something that can actually quench the cooling process. So because of that, there's a diffusion rate, because it is just all of a sudden of cooling, and you may have a different composition of phase in the end of the day, right? So we are still looking at the copper nickel phase diagram, because this is one of the simplest phase diagram for isomorphous. So consider 35% of nickel and 65% of copper cooling diagram from 1300. Okay, so the same. except that now we are looking at I think a non-equilibrium cooling. Okay, so we still have point A, B, C, D, and E and F, but I think this time we are looking at A prime, B prime, C prime, D prime, E prime, and also F prime. Right. So we are going to look at one by one. The first one is actually for A prime. Okay. So for A prime, you will notice that over here, okay, um, it is exists as a liquid phase. Okay. So since it is in the liquid phase, then there will be no microstructure. Okay. The composition is still the same as initial composition. It is still 35% of nickel. Okay. And I think you wouldn't have any formation of grains and whatsoever. So this is basically almost the same as I think the microstructure of liquid phase in equilibrium cooling isomorphous microstructure. Right. So moving on to B prime, you will see that there's a formation of small grains, okay, small grains of alpha. Okay. Alpha phase particles begin to form from the tie line with the composition of alpha is equals to 46% of nickel. Okay. So liquid is still 35 because it is located or overlap on the liquidus line. Okay, so it will be 35. Again, the same. But for the solid, you can drag it a bit. You can drag it here, and then you will see that the alpha composition is actually equals to 46% of nickel. Right. So C prime, okay, you will notice that the composition of solid and liquid alpha phase supposed to be 25%, supposed to be 25%. And uh, actually this is for liquid, L is actually equals supposed to be 29, and alpha is actually equals to 40. But due to the slow diffusion rate in alpha solid phase, the alpha phase form have not changed composition perceptibly. Okay, so it will be 46, okay, at the center grain to 40% of nickel at the outer grain parameters. So the average composition is equals to 42% of nickel. Okay, so uh, just want to maybe explain a little bit on this. So basically, as I told you, since this is a non-equilibrium cooling, what happened is that before the material will be how to say changed to another phase, or I think completely change its composition, it is not been converted completely due to the fact that it is been quenched, or the cooling process is quite fast. So what will happen is that the core center is still 46, okay, and you will have an outer layer. Okay, so if we look at point C, okay, the microstructure, you will have the grains layer that forms from D prime, which is actually equals to 46% of nickel. Okay, but after that, when it solidify, it forms another layer. So you will see that dia jadi macam donut lah. I mean, you have a core structure and you have an outer layer. So the outer layer is supposed to be 40. It's supposed to be 40 because if you read from here, the solidus line, it should be read as 40. But because of, as I said, the diffusion process is quite tricky because it's been facilitated, then the actual or the average composition is basically 42 or maybe 43. So how does it possible to form 42 or 43? Because you will see that over here, maybe instead of the solidus line is going this way, it is actually been dragged to go this way. But I think those who didn't know how to read the actual composition of the C prime alpha, you can actually, I think, calculate the average. Okay, so the average will be alpha is equal to 40 over here, 40 plus with the previous one was 46. Okay, and you divide with 2. So over here you will get like around maybe 86. Okay, so if you divide 86 with 2, you will get 43. eh? So this is actually the average or the actual composition of alpha in um, apa tu, non-equilibrium cooling. And if you ask me why we have to consider 43 instead of 40, as I said, because of it forms a layer, a layer of solidification. So you have a core structure of 46 and you have an outer layer of 40. So then the total composition will be the average of these two things. So you have like average of 40 plus 46 divided by 2, then you will get 43. Okay, so for liquid, it still be the same. There's no delay in terms of this. I mean, the liquidus line, it should be read the same as 29. Okay, but you will see that the microstructure for C prime is becoming like this. You have a layered structure. So you see that the nickel, I mean, over here, liquid is 29. The core structure is 46 and the outer layer is 40. But if the question asks, remember, in exam, if I ask you to to draw the microstructure, so you should draw the microstructure and put the composition as what you read from the phase diagram. So liquid is equal to 29, alpha or the center grain is equal to 46, and the outer layer you will read it from the solidus line, which is equal to 40. But if I ask you what will be the composition, you should actually write the composition of liquid is equals to 29% of nickel, and alpha is actually equals to 43% of nickel. Okay, all right. And then how about point D? Yeah? Or maybe over here we just see what the highlights. Level rule competition, more portion of liquid phase for non-equilibrium cooling. Solidus line shifted to the higher nickel content. Yes, as I said, since it is a non-equilibrium cooling, then the solidus line will be shifted a bit to the higher nickel content. All right, at point D prime, solidification is not completed, even though it's already here at the solidus line, okay? But it is not still completed. A portion of liquid is still remaining, okay? And the average composition of alpha is equal to 38. So over here, you will see at point D, the liquid composition is equal to 24 if you drag it to here. And then how about the composition of alpha? So the composition of alpha over here is 35 plus with the previous one. What is the previous one? So previous one was equals with 40. Okay, right. So you divide by 2. So this actually will give you 75, right? 75.2. So if you divide 75.2, you will get like what? The composition. It should be something berapa 30? 37 sorry. Isn't it? 37.5, right? Okay. Percent of nickel. Almost 38. Eh? So this is what it means. And if you look at the microstructure, you will see that the microstructure will form the center grain 46, the first layer 40, and then the second layer 35. Okay, because you read it from the solidus line. But the actual composition, this is actually the microstructure. If you want to draw, the actual composition, liquid is equal to 24% of nickel, and alpha is actually equals to 38 or 37.5% of nickel. Right. So it is actually the average of the previous composition, right? So what about E prime? So E prime, it is actually in the in the solid phase. Solidification reach completion. Suppose the last alpha phase to be 31% of nickel, okay? But the average now it becomes 35. So over here, still the same thing. It's already, in the solid phase. Normally, if we say that it is in the solid phase, then the composition will be equal to the initial composition, which is the C prime, which is 35 lah. But in this case, because we are talking about non-equilibrium cooling, then the alpha is still considered not, almost completed. Then alpha is still to be read as 31. Okay. Then if you look at the microstructure, you will have liquid is equal to 21. Okay. The grain or the core grain is equal to 46. First layer 40, second layer 35, third layer 31, and the average I think composition is actually equals to 35 lah. Right? So still 35. Right? We still consider it as to be similar as the composition initial, right? And finally, for F prime, it would be a totally solid materials. Okay, unlike equilibrium cooling, it will form polycrystalline. But for F prime, it will form like this size. Like a contour micro structure. You will see the core grains 46, first layer 40, second layer 35, third layer 31. And this is actually upon completion, right? All right. So any questions so far regarding on non-equilibrium cooling microstructure? Is there any question? Any doubts? Probably in terms of calculating the average composition. All right. So the slower the cooling rate, okay, the smaller the degree of displacement with regards to the difference between equilibrium solidus and average solid composition. Okay, and we have two important terms in non-equilibrium cooling isomorphous microstructure. First one is known as segregation. So what does it mean by segregation? So segregation is actually the formation of non-uniform distribution of two elements within the grain. So that is why you will see layer by layer. This is actually due to the segregation. And there's also cord structure. Cord, truss, kita cakap to truss, cord structure. The center of the grain, which is rich with high melting elements with less optimal properties. So this is actually forming first before you have a layered structure. So the cord structure is the one that has a very rich in high melting element because it has higher percent of nickel composition, for example, and also less in optimal properties. So coring may be eliminated by homogenization heat treatment at temperature below solidus line. So this process, the atomic diffusion will occur and produce compositionally homogeneous grain. So it means that when you do or when you have produced non-equilibrium cooling isomorphous alloy, it is still possible to make it homogeneous. So how to do that? As mentioned, you have to reheat it again. You heat it again and you just put it at the slow cooling. Then only it will form the equilibrium cooling isomorphous alloy. Right? So the cord structure versus equilibrium phases. So the composition of alpha was observed to be changes as it solidified. This is actually in terms of non-equilibrium cooling. And for the copper to nickel case, you will see that the first alpha to solidify has a very high percentage of nickel, and last to solidify has I think around 35 as equals, as the same as the initial composition as, right? And this is actually to compare the microstructure of alloys that produced from equilibrium cooling and also non-equilibrium cooling. So for non-equilibrium cooling, you will see that it forms a layered structure, okay, with a core structure of 46% of nickel, and I think the outer layer is the last to be solidified. Meanwhile, for equilibrium cooling, you just see only like homogeneous, only one phase that is formed. Huh? All right. And in terms of mechanical properties, as you actually produce the different types of alloy with different composition or different amount of nickel or the other elements, you will see that it will actually reflect to the mechanical strength of the alloy produced. For example, over here, if you actually increase the composition of nickel, okay, up to 100%, at certain point at 60%, you will see that the tensile strength will be the optimum, and after that, it will actually decline. So you will understand more about the tensile strength diagram, this in the next chapter in mechanical properties. But what I can explain earlier over here is that the material, the metal is actually having the initial of elastic deformation, elastic deformation. Okay, so what does it mean by elastic deformation? So elastic deformation is if you imagine you have like one metal bar, you pull it both end, and after that, okay, it still remain. If you release the force, it still remains the same. Okay, right. But after certain time, okay, as you increase the composition and as you increase the tensile, what will happen is that it will form a so-called plastic deformation. Okay, so plastic deformation, it means that if you have now uh, one metal bar that you pull both ends, so what will happen is that it will elongate. Okay, so it will elongate and it will not return back to its original shape. So this actually what we call it as plastic deformation. Okay, macam kalau if you notice metals, if you just pull it with a small force, it will return back to its size. But if you have a strength and the composition you actually increase, if you pull it, it will be elongate. Okay, it will actually experience plastic deformation, and after this, over here, it will actually experience the so-called ultimate tensile strength, the optimum one, the ultimate tensile strength. And finally, it will drop. So this actually happens if the materials experience necking and breaking. Dia dah memanjang and then after that, it breaks. Okay. All right. So for ductility, also the same thing. It is actually in contrast with tensile strength. As you actually increase the composition up to one point that you see that the elongation will be the lowest, okay, and after that it will be increasing again. All right, so before we move on to the next part of a phase diagram, is there any questions so far? Ada soalan? Ada apa-apa yang nak ditanyakan? Okay, all right. So we move on to the next, I think, parts of phase diagram. So earlier we have understand about isomorphous system. Okay, and as I told you, to get isomorphous alloy, okay, it needs to fulfill the requirement of Hume rotary rules. But what happens if the material doesn't follow Hume rotary rules? So that is why it will produce a different types of alloy, which we will discuss it now. Okay. So part of it is actually known as eutectic system. Okay. So binary eutectic system is part of it. Okay, so what does it mean by binary eutectic system? Binary, it means that it's still composed of two elements or two components. Okay, and eutectic system actually means that it has a special composition which the material melts, or the uh, the solid melts or the liquid solidify at a very low melting temperature. Okay, so most of this eutectic system, actually you can see it a lot in soldering materials. Okay, bahan-bahan pemateri. Okay, for example, copper, silver, lead, tin, and whatsoever. Okay, for example, over here it mentioned or it shows the phase diagram of copper, silver. Okay, copper, silver. Then you will have this kind of shape of your phase diagram. So remember, the most important things in binary eutectic system is the equation or the reaction. Because over here you will see that when you have the molten elements or component together, when it solidify, it actually forms another two solids. One liquid, when it solidifies, it forms two solid. So this is actually a very straightforward definition of uh, binary eutectic system. Okay, so one liquid, when you solidify, it will become two solid phase. Liquid equals to alpha plus beta. So this is actually a very classical equation for eutectic reaction. Okay. So over here, to understand the phase diagram clearly, you will see that at one end, okay, of the sides, you will see that there's a formation of alpha solid phase, and at the other end, it forms beta solid phase. Right, on the top, it's still liquid, and in between each phases, it will actually have a mixture. Like for example, over here, you have a liquidus line, and this is actually the solidus line of alpha, and this is actually the eutectic temperature, TE. TE is actually known as eutectic temperature. As what I told you for eutectic system, okay, this alloy actually have a special composition that melts at a lower or minimum melting temperature. So over here, okay, you have a mixture of liquid plus alpha. It still have a solid, it still have a liquid, but I think beyond this temperature, you will have only one solid, and the solid will be a mixture, alpha plus beta, right? Okay, so in between beta also there will be a mixture of phase, liquid plus beta. Okay, and then the composition of eutectic is known as Ce. Okay, so Ce actually exists in the overlapping lines of uh, the liquidus line. So this is actually known as the invariant point, the intersection line, and the composition of eutectic is equal to 71.9 for copper silver. And over here, okay, for the eutectic line, you will see that it will actually overlap with the solidus line of alpha at 8%. Okay, meanwhile, the other ends, of eutectic line, okay, it will actually overlap with the solidus line of beta at 91.2. Therefore, if you want to write, okay, the binary eutectic reaction equation, it will be something like this. You should actually write the composition. So LCE, okay, double head arrow. So double head arrow actually means heating process and cooling process. Cool and heat. Then you have alpha. Okay. So this will be C alpha plus beta, and this will be C beta. So what will be the composition? Now from this phase diagram, you will see that L is equals to 71.9. Okay. So double head arrow. You can write the temperature over here. The temperature mentioned is around almost 800 lah. Maybe I just write 798 degrees C. Then you have alpha of 8% silver. Sorry, this one is 71.9% of silver plus beta, which is equals to 91.2% of silver. Okay, so this is actually the representation of binary eutectic equation reaction. So normally during exams, I would love to ask this kind of thing. So what is actually the eutectic temperature? So you should read from the phase diagram. Okay, eutectic phase diagram. You just look at the flat line over here, the horizontal line. So just read what is the temperature over here, and what will be the eutectic reaction. So you should write, okay, the liquid that forms alpha plus beta, and together with its composition. All right. Okay, so now how actually we are going to interpret the phase diagram of a eutectic system. Okay, for example, over here now we are having an examples of lead tin phase diagram. Okay, if you notice the phase diagram pattern as compared to copper silver phase diagram, it resembles the same thing. Bentuk dia nampak sama, betul-betul exactly the same. Okay, you will see that you will see that the phase diagram, if you allow me, maybe I can set the slide. Okay, you will see that it has one solid phase, two solid phase in between, and then so you have liquid on top, alpha, beta at the other ends. Over here, this is actually liquid plus alpha. Why over here is liquid plus alpha? Because the border is actually the border of liquid and also alpha. Meanwhile, over here, it will be liquid plus beta. And at the bottom, it will be alpha plus beta. Still the same thing. So this is actually the eutectic temperature. This is actually the composition of eutectic. This is actually the composition of alpha. And this is actually the composition of beta. So still, we are looking at the reaction. So L double head arrow is equals to alpha plus beta. Okay, and you should actually put the composition of alpha and composition of beta over here. Okay, all right. So you will see that it forms the same pattern, even though now we are looking at lead tin phase diagram. So for example, you have 40% of tin and 60% of lead alloys at 160 degrees Celsius. So find number one, the phases present. Okay, so don't look at the answer yet. So try to understand the question first. So over here, the question asks for 40% of lead tin. Okay, this is actually information number one. Information number two, it gives the temperature which is equals to 150. So first, what you need to do, so just find 40% of tin over here. So 40% of tin, you just draw the straight arrow here. 150 after that. So you know that this is actually the point. This is actually your point. So what would be the phase over here? Can someone ask? Sorry, ask. Can someone answer that? Apa point dia? Saya nak tanya Ani Zulaika. Ani Zulaika, ada tak? Tak ada. Ani Zulaika tak ada. Hasnun. Hasnun ada? Hasnun pun tak ada. Dalam bah kot. Okay. How about Chia Chun Oi? Chia Chun Oi, are you there?
Yes.
Okay, alright.
Yes.
So what would be the phase at 40% of tin and
Sorry,
at 40% of tin and 150 degrees C?
at 40%. Oh, okay. At 40% is alpha plus beta.
Alpha plus beta. Okay, alright. Thank you very much. If let's say that I
It's
ask,
alpha plus. Yeah. Okay.
okay. If let's say that I ask another person, okay, siapa tanya Liu Li Jing. Liu Li Jing, are you there?
Yes, doctor.
Okay, right. So if let's say that I ask you now at 70% of tin, 70% of tin and 210 degrees Celsius. So what would be the phase?
Liquid.
Liquid, Leah.
70%.
70%.
Is
Okay.
it liquid plus beta or liquid? Because I don't know 210
Yeah.
is.
Okay. Okay lah. I also okay. It's okay. So it will be somewhere here lah. Then liquid. Okay. Thank you very much. Maybe another person. Boy pula. Muhammad Hakim. Muhammad Hakim Azhan ada? Okay, Hakim. Saya nak tanya, okay. 30% of tin and at 250 degrees C.
Liquid plus solid.
Liquid plus alpha. Solid dia ada dua sekarang ni. So you have to refer which one, alpha or beta?
Alpha.
Alpha. So 30% over here. Okay, and let's say that 250 somewhere here. Okay, so you get the phase will be liquid plus alpha. Okay, so good. I think everyone now able to identify the phases. So next, the question asks, what will be the composition of each phase? Okay, so since the question over here now is 40% at 150, so you know that it is actually the phase. Phase is equals to alpha plus beta. Okay, and remember, when you have a mixture of phase, you need to report the composition for both. Meaning that over here, you should actually report what will be the composition of alpha and what will be the composition of beta. So how to do that? Okay, so still the same thing. Okay, you draw the tie line. Okay? You drag the line until it overlaps with the solidus line of alpha. Then you will get the value. So this will be your C alpha. And then for beta, you just drag another line that touch the solidus line of beta, and you will get this is actually your C beta. So you get 11% of tin for C alpha and 99% of tin for C beta. All right. So next question, because this actually three questions. So one, phase, second, composition, third, okay, amount. Okay, so what would be the relative amount of each phase? All right. So over here, we already identified the composition of alpha and beta. Okay, and we want to calculate now what would be the weight fractions. Okay, since as I said, the phase still exists at alpha plus beta. Now, for the weight fraction, you need to report the weight fraction of alpha and also weight fractions of beta. And in order to do that, we still use lever rule. Okay, all right. So how to do? Okay, if you notice, after you have drawn the line R and S, let's say that you want to determine the composition, the weight fractions of alpha. So alpha is located on your left. Nampak alpha ni dekat sebelah kiri. So what will be the opposite line? Of course, the opposite line will be S. So that is why over here you will get the formula is S over R plus S. Meanwhile, for beta, beta is located on your right hand side. The opposite line for beta, okay, is actually R. Okay, then the formula to calculate beta weight fraction is equal to R over R plus S. So if you calculate, okay, so since we already identify beta and we know that C naught is equals to 40, then you can actually calculate 99 minus with 40 over 99 minus with 11. So you get the answer. Okay, and remember, for each question, if the question didn't ask to give in percentage, you should give in decimal. It should be 0.67. So if the question asks what's the percentage amount, then only you write it as percentage amount. So beta, the same thing, R over R plus S. So you just substitute. Okay, so R is actually the length. Okay, so C naught minus with C alpha. So 40 minus with 11 over 99 minus 11. Then you will get 0.33. Okay, all right. So is it clear? Okay. So I guess maybe I just want to give a try lah kepada to you guys. Let's say can I delete this? Okay, yes, can. Okay, all right. So we do another practice, but this time we look at a different percentage. All right. So maybe the same thing as what I asked to Hakim just now. At 30%, 30% of tin, and temperature is at 250 degrees C. Okay, so just now, if we look over here, 30%, 250. Okay, so you get, I think the points here, and the phase is actually equals to liquid plus alpha, right? So now I'm going to ask, number one, the phase already been asked, what will be the composition? Number two, what will be the weight fraction? Okay, so saya nak cuba panggil someone. Okay. Alright. Siu Sui Xiong, are you there?
Yes, doctor.
Okay, all right. So, can you actually identify the composition for that point? Right, and another person. Tan Si Leong. Tan Si Leong, are you there?
Yes, doctor.
Okay, can you actually identify what would be the weight fractions for that one? Okay, right. So the first one, I think first one tadi siapa? Forgot the name. Siu, Right. So have you actually identified what would be the composition? Just roughly.
Yes, doctor.
Okay, so what is it? So what would be the composition that you are looking at?
The composition of liquid and alpha.
Okay, good.
So
Right? Because we know that it exists in the phase of liquid plus alpha. So the composition that you should report is the composition of liquid and also the composition of alpha. Okay, so what will be the values approximately?
For liquid, the composition is about 33%. 33%.
33, eh?
Uh,
Okay, so you can drag somewhere here, okay, when it overlaps with the liquidus line, just drag it down. I think maybe slightly above, maybe I would say like 36% lah, for example, thin. And how about alpha? Roughly? Two?
about 15% thin.
Got 15. Oh, saya pun saya ingat juga ni. Yes, maybe around 15 lah. 15% of thin. Okay, very good. Okay, so because now we are not talking about the alpha beta, because now we are in liquid plus alpha. Then the composition will be one composition of liquid, another one is composition of solid alpha. Okay, so next one, Tan Shi Leong.
Oh, yes, doctor.
Okay, so have you identified, okay, since I think with the information provided with the composition, what about the weight fraction? What kinds of weight fraction that you are looking at?
Wave fraction for alpha.
Okay, so weight fractions of alpha. And another one?
Wave fraction of beta.
Beta? Are you sure? Okay, so since I've told you that for this question, we are looking at 30% of tin at 250, okay? So the phase is actually liquid plus alpha. So for the composition, we need to report the composition of liquid and also the composition of solid alpha. Even for the weight fraction, we need to report the weight fractions of liquid and also weight fractions of alpha. So maybe for this one, it would be weight percent W alpha and another one WL or liquid. All right. So how to do that? Maybe you need to, again, to draw a tie line R, and over here is S. So since over here we already identified this will be around 15, and this one is 30 and this one is 36. Okay, right. So if you want to calculate alpha, W alpha, so what would be the formula?
36 minus 30 divided by 36 minus 15.
Okay, very good. Okay, so alpha is located on your left hand side, so the opposite line will be S. So S over R plus S. Okay, so it's a good tip if you write the formula, because during exams also, if you answer it wrongly but you put the formula correctly, then I can give you marks also. I mean, just mark kesian lah. Okay, so just now you mentioned 36 minus with 30 divided by 36 minus with 15. So what's the value that you get? Did you check? Not yet.
Wait, 0.29.
0.29, Okay, all right. So for weight fractions of liquid, now liquid is located on your right hand side of this line, of the tie line, then it will be R over R plus S. Okay, so what's the value? 30 minus with 15 divided by 36 minus with 15. Isn't it? Yes.
Yeah.
So what's the value? 0.71, right?
So yeah.
Okay, right. So even if you got this one, if you still remember W alpha plus WL, if you sum it together, you get 1. If you get like 1 of it, you still can like 1 minus with 0.29, you get 0.71. Okay, all right. So I guess it's quite clear enough for everyone for this, I think, binary Eutectic system, probably in terms of getting the composition and also weight fractions. And still, I think, remember, if you want to, I think, check or probably read, if you have any problems or what, you can actually come back to me and we can discuss it again. Right. So I guess maybe for today, because there's also another thing that I want to show regarding on the volume fractions. Just now we are talking about weight fractions, but we have not looking at volume fraction, how we can calculate volume fractions. But I believe maybe this one is after your mid-semester break lah. Okay, so at least for today you are able to understand how to process or how to read the binary eutectic phase diagram and how to calculate the weight fractions of every phase that you read. Then this should be enough at the moment. Okay, so as I said, I already posted your quiz on the e-learning, so perhaps you can spend some time to look at it and maybe to submit it today as well. And if you have any problems or anything, still you can communicate with me. Then maybe I can open for question if there's any question before I join the class. Anything? Any question? All right. So if there's no further question, then I will adjourn the class. Thank you very much for your kind attention. I wish you a happy holiday, 1 week holiday. So next week, no lecture. If you want to have a lecture, I think just tell me. We will set. No, just kidding. Okay. So we will see again after next week. Okay, so thank you very much, guys, and my regards to your family. Safe trip, and hopefully we'll meet again after 1 week. So goodbye, and assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.